So, as far as design of combinational logic is concerned, particularly this digital combinational circuit. So, we take help of certain design techniques. So, we will take a small example and elaborate it, and that way you will be able to design any other circuit as well. So, the example that we take is something called a 3 input majority gate, 3 input majority gate. The idea is that we have to design a block where there are 3 inputs. If this is the block that we design, now there are 3 inputs, say A, B and C, and there is a output. Now, this block will produce a value 1 when the majority of its inputs are equal to 1, otherwise it will output a 0. So, any combinational design, it starts with the truth table of the design. So, if we take the truth table, try to draw the truth table. So, we have got these 3 inputs A, B and C and the output as F. So, if you take this combination 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1, then it as the statement of the problem said, the majority of the inputs should be reflected. So, this majority is 0. So, this is 0, this is also 0, this is also 0. So, this is 1, this is also 0, this is 1, this is 1 and this is 1. Now, once we have drawn this particular table or the truth table, the next important thing that we have to do is making something called a Carnot map. So, we have to arrive at the logic expression that can be used for this particular block. So, that is done by means of Carnot map. So, in a 3 variable Carnot map, so it will look something like this. So, on one side we put the variables A, B, other side we put the variable C, and these are the combinations. So, 0 0, 0 1, 1 1 and 1 0. So, this is 0 and this is 1. Now, wherever this is a the output is for 0 0 0 it is 0, for 0 0 1 this is again 0, then 0 1 0 is also 0, 0 1 1 is 1, then 1 0 0 is 0, 1 0 1 is 1, 1 1 0 is 1 and 1 1 1 is 1. So, this is the Carnot map. Now, after drawing this Carnot map from our digital logic classes, so you can find out that we have to make the groups of these ones, and we will try to make as large a group as possible. So, in this particular case, so we can make groups like this. So, this is one group, so this is another group and this is another group. So, if we do this, then this will be giving me the expression. So, when you are checking say this group, so this is A B, this is A B, then if you are taking say this group, then it is the bit A is not changing, A C, and if we are taking say this group, then it is B C. So, A B plus A C plus B C. So, looking at the expression, you can immediately find out that this is correct, because our objective is to find majority of the inputs to be 1, then only the output will be 1, and each of the here the A and B both are 1. So, naturally that is the majority outputs, and A and C both are 1 and here B and C both are 1. So, that is the majority function has been represented properly. Now, you can draw the corresponding digital logic circuit, combinational circuit by these are AND gates. So, for realizing this product terms A B, A C and B C. So, you can take it like this. So, A B, A C and B C, and there is an OR to sum them up. So, this is the OR gate where I am connecting all of them. So, this is the function F. So, this way for any digital design, so if it is a combinational design, so you can take help of this truth table and Carnot map to arrive at the logic expression. Sometimes it is this Carnot map problem is that if the size number of inputs is large, more than 4, it is difficult to draw the Carnot map on a piece of paper. So, it becomes problematic. Of course, there are other methods by which you can do this type of minimizations or optimizations. So, that you can find out in digital logic classes. So, next thing that we will look into is the sequential part. So, sequential okay, before sequential part. So, there is another very common circuit that is used in microprocessors and microcontrollers, which is the adder circuit. So, we will look into this adder circuit carefully, because this will be again used repetitively in any of these processors. Okay. So, what does an adder do? So, adder, it will add the bits. Okay. So, this adder you can classify into two, as far as the design is concerned. So, you can classify it into two classes. One is called half adder and the other is called full adder. This half adder, it just adds 2 bit. So, this half adder block, if you try to see this half adder, it has got 2 inputs A and B, the bits to be added, and it produces 2 output, one is sum, other is carry. So, this is sum and this is carry. Okay. So, the truth table, so this is a combinational circuit. So, I can represent it in the form of a truth table. So, if I want to do this thing, so this A, B, and I have got this sum and carry as the 2 outputs. Now, combinations are 0 0 0 1, 1 0 and 1 1. So, this sum, so in this case both are 0. Here the sum is 1, carry is 0, here also the sum is 1, carry is 0. In this case sum is 1 and the carry is also 1. Okay. Sorry, this sum should be 0, because if I am adding 2 bits 1 and 1, so when I am adding them I will get the result as 0 and with a carry generated. So, this is the carry and this is the sum should be 0. So, you see that if you represent it in the form of a Carnot map for the sum part, so it will be like this A B. Okay. So, for 0 1 and 1 0 the output is 1. So, these two are 1 and these two are 0. So, you cannot group this ones in any way. So, you get the expression as A B bar or A bar B. So, that is nothing but A XOR B. So, this symbol we use for XOR. So, A XOR B. For the carry part is you see that it is basically the AND function. So, this is the sum, and the carry part is nothing but A B. The carry part is A B. So, I can realize this half adder like this. So, there is one XOR gate, where this A and B inputs are coming, here, and there is one AND gate where this A and B inputs will be fed. So, this is the sum output and this is the carry output. So, we have got this as the half adder block. Okay. Now, this half adder, the problem is that it can add only 2 bits. Okay. Now, if you want to add 3 bits, then we get something called a full adder. So, the full adder part. So, as far as the block is concerned, so it has got the inputs like this A, B. There is a third input which we conventionally call carry in, to indicate that this is the carry input from the previous stage of the adder, and the sum we have got sum output, and for this stage we have got the carry which we call carry out, that is the carry of the current stage. So, this is the full adder. Now, if you represent in the form of truth table, so it will be like this: A, B and carry in, and here you have got this sum and carry out. Now, if it is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So, these are the combinations that we have. Now, for that, so here the sum output will be 0, carry will also be 0, here sum will be 1, carry will be 0, here also sum will be 1, carry will be 0, here sum is 0, but carry is 1, because when you add this A, B and C in, so this 1 plus 1 will be 0 and a carry will be generated. So, carry output will be 1. Here again the sum is 1, sorry, here again the sum is 1 and the carry is 0. Sum is 1 and the carry is 0. Sum is 1 and the carry is 0. Now, here again you have got sum as 0 and carry as 1. Here again you have got sum as 0 and carry as 1, and here you have got sum as 1 and carry also as 1. So, we have got the truth table like that. So, you can design this function, and get the corresponding internal circuit. The other way of doing the same operation is by means of using the half adder. Like we have got one half adder, that adds the numbers A and B, and it produces the carry and the sum outputs. Now, this sum output, it can be put into the next stage of half adder. So, the sum comes here and the carry input that we have here, the C in can be put here, and this gives me the final sum. So, this is the final sum, and this carry, you see, I can take one OR or NOR gate and I can take this carry generated like this. So, this is the final carry. Okay. So, this way I can have the final carry generated by doing the using half adder. So, we can get this thing. Now, so this way I can add two 1 bit numbers, okay, with the carry also. Now, if you want to add numbers that have got more number of bits, like say suppose I want to have say two numbers A and B, where A is say 4 bit. So, A3, A2, A1, A0, these are the 4 bits, and the number B, it has got again 4 bits, B3, B2, B1, B0, and I want to add them. Now, how to do this addition? Okay. So, you can add, you can have full adders for doing this job, like you can have this the first stage of the full adder. So, it can be given the responsibility to add this A0 and B0. It can be given the responsibility to add A0 by and B0. So, this is a full adder. So, it will produce a sum which we call the 0 bit of the sum S0. Next stage of the full adder, it can add the digits, it can add the bits A1 and B1, and accordingly it can produce the bit S1. The next stage can add A3 and B3, A2 and B2, and it can produce the output as S2, and finally I can have this A3 and B3, going there and producing the output S3. and there is something the carry part. So, for this one the carry in is made equal to 0. So, this is the carry in. So, this is grounded because it does not have any value. So, this is carry, there is no carry input here. Now, this carry output can be fed to the carry input of the next stage. Similarly, this carry output can be fed to the carry input of the next stage. So, this can be fed as the carry input of the next stage, and finally, so from the last stage you can generate the carry signal for this entire 4-bit addition. So, this way we can utilize this full adders, combine them to a large size and accordingly get the adder circuit for larger number of bits. Of course, this is this type of adder that I have discussed. So, this is commonly known as ripple carry adder. They are known as ripple carry adder because the carry bit is actually passing through all the full adder stages. Now, so that way the delay of this circuit is quite high, and most of the processors they will use some improved version of this adder. Okay. So, if you look into some book on VLSI, so you can find out what are the different types of adders that are available. So, the most the fastest adder that we have is the carry look ahead adder, the carry look ahead adder. So, where these carry bits are computed beforehand, and that way it does not need to this like this stage here. So, this stage, so it has to wait for the the previous stages to finish off, and then only the carry is available here. So, that this full adder can do the operation. Whereas, in carry look ahead adder, so this carry propagation is not required. So, it is calculated beforehand, and that way the operation becomes faster, though the amount of logic involved in the circuit is more. Okay. So, this way we can go for this adder circuits. Next, we will look into another class of components that will be required in the design of these processors, which are known as the sequential circuits. The basic block of any sequential circuit is called a flip flop, okay, because flip flop is a module that can remember the previous stage, like unlike combinational circuit. So, like in case of say one AND gate. So, if you take an AND gate, so it AND gate whatever be the current input, based on that it is giving the output. So, it is not remembering anything about what was the past output of the AND gate, but sometimes it is necessary, but we need to remember the information about different the previous stage of the circuit. So, that way it can be done by means of another class of circuit called flip flop. So, the simplest type of flip flop that we have is the D flip flop, where there is a D input or data input, and there is a Q output or the so normally there are two outputs, Q and Q bar, where Q bar is the complement of Q. Now, some of the cases you may not find the Q bar output explicitly, but it is in many cases. So, Q and Q bar are there, but in some cases some logic libraries may not have the Q bar output. Another very important input that we have here is the clock signal. So, this clock signal controls the operation of this flip flop. Okay. So, we have got the clock signal. So, it is represented often like this. So, we call this the clock pulse or clock signal. So, the operation is like this: whenever this clock pulse comes, then the value of this D will be copied onto Q, and Q bar will get the complement of that. And if this clock pulse is not there, so it will remember the previous value. So, in terms of truth table, you can say that if it is D and it is Q, if the D bit is 0, then this Q will also be 0. If D is 1, Q will be 1, but all of these are true provided the clock pulse value is equal to 1. On the other hand, if the clock pulse value is 0, whether it is 0 or 1, it does not matter. So, the clock pulse value is 0. So, it will continue to have the previous value. So, you can say Q n minus 1, q n minus 1, that is the previous value of q. So, it is not dependent on the value of d. So, if the clock pulse is absent, then nothing happens to the circuit. So, it continues at the with the previous, it continues with the previous value, remembers the previous value. Okay. Now, how to realize this circuit? So, for realizing it, so you can do it in terms of combinational gates. So, we can do it like this, say I will just draw the circuit, then I will try to explain. So, we have got this D input here and we have got this clock pulse going to both of them. So, D is connected there and D bar line is connected here. Okay. And then there are two cross coupled NOR gates. There are two cross coupled NOR gates to realize the Q and Q bar lines. Okay. So, this is connected like this. Okay. So, this is Q and this is Q bar. Now, you see that if the clock pulse is 0, then what happens is that both the lines will get, both the NAND gate outputs will be 1, and as a result this Q bar coming here will get inverted and it will remain as Q. Similarly, the Q comes here getting inverted and remaining as Q bar. So, that way it continues as Q and Q bar. So, if the clock pulse is 0, nothing happens to the circuit. If the clock pulse value is equal to 1, then at this point you get the value of D bar and here you get the value of D, because D bar comes here, that is inverted. So, you get the value of D. Now, the D bar coming here. So, if the D value is equal to say 1, then this D bar is 0 and then this value is say 0 and whatever is the Q bar. So, in that case it will be, if this value was, if this value was previously 1, this value was 0. Now, so this 0 and 0, so this is not, so you will get a 1 here, and if it is 1, then you will get a 0 there. So, that way it is getting the value of D bar at the Q bar line. Okay. So, like say this D bar line, D is, if D is 1, D bar is 0. Now, this is the NOR gate. So, this 0 and this Q bar. So, you will get a, the Q bar line will be coming here, Q bar line will come here, it will get inverted and it will remain as Q, and otherwise it will change to Q bar. Now, so we can have this this combinational circuit. So, it can be used for realizing various module, like we can realize something called a comparator. Can realize something called a comparator. So, in a comparator, what happens is that the basic comparator module. So, if I want to compare between the numbers A and B, where A and B, so both are 4-bit numbers. So, this is say A3, A2, A1, A0, and this is B is B3, B2, B1, B0. Now, if I say that the comparator has got a number of outputs equal, greater than, less than, like that. Okay. No, so this so as far as the block is concerned, so it is like this, that it has got this A and B inputs, which are each of them are 4-bit, and then it has got 3 outputs, EQ, GT and LT. Now, you see that you can always draw the truth table. Okay. So, if you try to draw the truth table, then there will be 8 columns here and total 256 rows will come in the truth table, and you can realize it, you can find out the condition of equality, greater than, less than, and accordingly you can draw the circuit. On the other hand, you can also apply your intuition and try to come to the circuit. So, the equation for say for the equality part, so equality will be true when all the bits are same, and when all the bits are same. So, you have got this x NOR gate that will represent this operation. So, if you say it is A 3 x NOR B 3 and A 2 x NOR B 2 and A 1 x NOR B 1 and A 0 x NOR B 0. So, if all the bits are same, then this x NOR output will be 1. Okay. So, all these sub terms they will evaluate to 1. So, EQ will become equal to 1. On the other hand, if you are trying to get the value of expression for GT, okay. So, GT, so A is greater than B, the first condition is that if A 3 equal to 1 and B 3 equal to 0, then you have got A greater than B. The first condition is A 3 B 3 bar, A 3 is equal to 1 and B 3 equal to 0. The next condition that you have is A 3 and B 3 are same, but A 2 is equal to 1 and B 2 equal to 0. So, the next condition that you have is A 3 x NOR B 3. So, A 3 and B 3 are same, and after that you have got A 2 B 2 bar. So, this is the next operation, this is the next condition for this term to for j greater than term to be true. Or third condition is that A 3 B 3 A 3 and B 3 are same, A 2 and B 2 are same, but A 1 is 1 and B 1 is 0. So, you can accordingly write this expression A 3 x NOR B 3, A 2 x NOR B 2, and then you have got A 1 B 1 bar, and finally, you have got all the bits same, only the 0th bit differ. So, A 3 x NOR B 3, A 2 x NOR B 2, A 1 x NOR B 1, sorry, A 1 x NOR B 1, and then you have got A 0 B 0 bar. So, these are the conditions for GT. So, this way you can write down the expression for less than as well, and you can realize it using the circuit. Okay. So, the comparator circuit can be designed in this fashion. So, you can also use this concept to realize sequential circuits, like you can have so we have seen how to realize a single flip flop. Now, in computer, in processors, there is one module which is called a register, which is very common in all these processors. So, register means it is instead of having a single flip flop, you have got a collection of flip flops. So, I can have a 4-bit register. So, if you want to get a 4-bit register, so you need to have 4 flip flops. Okay. So, 4 such D flip flops can be there. So, conceptually we will represent it in this fashion. So, this is my 4-bit register. Okay. So, this is the 4-bit register. So, it will have 4 input pins, 4 input lines, and can have 4 output lines. But actually what happens is that if these are the 4 flip flops, so the input, actually the first input comes to the first flip flop, second input goes to the second flip flop, third input goes to the third flip flop and the fourth input goes to the fourth flip flop. Similarly, as far as the output is concerned, so this is the first output, this is the second output, this is the third output and this is the fourth output. So, that way they come. So, these 4 bits that I have shown here, so they are actually the 4 input lines here. Similarly, the 4 output lines that I have shown here, the 4 output lines here. So, what is common between all these flip flops is that they are the clock line that they have. So, the clock line should be common. Okay. So, all of them have got the same clock line. So, they operate at the same clock they operate at the same clock. Fine. So, this type of registers, so they are called parallel load registers. So, this 4 bit pattern can be loaded into these registers or you can read from this register. So, this register is another common component that we have in the processor design.